Welcome to another exciting session with Temple AK Academy. Today we're dealing with this beautiful topic in mathematics known as indices. Indices goes along with surds and logarithms. It's a very important topic that will always occur in problem solving in the whole world of mathematics. Straight away, let's get into it. We're looking at what an index is. An index generally is the power to which a number is raised. A number raised to a power. The power to which the number is raised is known as the index. Let's start straight away. We have a number represented by A, and we have a power on it, X. That power to which the number is raised is what we call the index, and the plural is indices, as we have observed in the definition. So this is the index. So our studies is about manipulation of these indices. Now the number, we must remark right away, the number raised to that particular power is known as the base, the same way we encountered it in the studies of logarithms. So you have to get that video on logarithms and study and enjoy. There are other terms that describe index. So simply, it is the power to which a number is raised. And there is, of course, another word. The word exponent also describes index, exponents. All right. So much for that. Now, the interactions of indices are based on special laws. So the next area to consider is laws of indices. Come with me. Let's get straight into them. Let's go. All right. Okay. Now, the laws of indices straight away, for which we can start with the first one. Let's go. The first law is the simplest of the laws. This law says any number raised to the power 0 gives 1. So we have a general number represented by A, and we raise it to the power 0. The result is simply 1. Very simple law. No matter the size of the base, the number being raised to the power, the answer is simply 1. If we have 1,000, 1,000, as large as it is, so long as we have raised to the power 0, the result is 1. So the point to observe here is the power. Once the power is a 0, then the answer is 1. All right. Very simple law indeed. So let us look at the second law. We get the traces out of the way. For the second law, it is a combination law, of course. A combination law, a law that helps us to combine indices. Now, supposing we have a number raised to a power, a certain power, multiplied by the same number raised to a different power. Here we have the bases being the same. That's the base A in the other writing. So the law of indices requires us to take that same base that has been raised to different powers, and then we define a new power by addition of the original power. So X is added to Y. So the same base, but raised to a power given by the sum of the original powers. Let's have an illustrative example straight away. Supposing we have 2 to the power 3, multiplied by 2 to the power 2. Now we inspect very quickly the same basis. We have 2 to different powers. So we're going to combine this. This is a combination law. We take that same base 2 and have a new power defined by the addition or the sum of the original powers. So we have the first one 3 plus the second one 2. And this gives us 2 to the power 3 plus 2, and that's 5. Now we need to evaluate this. What's the interpretation here? 2 multiplies itself 5 different times. So in the rough area, let's see, 2 multiplies itself 5 different times. What will be the result? Naturally, practice will help you to know that 2 to the power 5 is 32. But how do we have that? 2 multiplied by 2 gives us 4. The 4 resulting times 2, 8. The 8 resulting times 2, 16. The 16 resulting finally now times 2 gives us the final result, which is 32. So all the powers of 2 up to 10 will be borne in mind. Practice will help you do that. So the final result here is 32. Beautiful. Let's get into the third law. The third law is also a combination law. So let's go for it. Now we have our traces out of the way. Combination law, which involves division this time around. So we have the number A raised to the power X, now divided by the same number, that's the same base, raised to a different power Y. Another way to write this is to have the number A raised to the power X, now divided by the same number A to the power Y. How do we go about this? The bases are the same. As we can see, a being raised to the power in the first writing, the same a being raised to power in the second writing. As we have observed also, it is the a to the power, and it is a right there, which means the results start with taking that same a now to a new power given by the difference. So the power in the numerator subtracts the power in the denominator. That's the law. So we have x minus y. Very simple. Very, very simple. Let's have an illustration. Supposing we have 2 to the power 5 divided by 2 to the power 2. How do we go about this? We can already see the bases are the same, 2 to the power, 2 to the power. And the law of indices requires us to say that same 2 to which both the numerator and denominator have been raised as powers, given by the difference in the power. So we have the power in the numerator 5 up, minus the power in the denominator 2 down, and gives us 2 to the power 5 minus 2 straight away is 3. And 2 to the power 3 gives us 8, of course. Very simple. 2 to the power 3, 2 has to multiply itself 3 different times. And you can easily find that, of course. 2 times 2, that gives 4. That 4 resulting times 2 gives us the expected 8. Very simple. All right. So much for that. Let us move on. Another law awaits us. Law 4, of course. The law 4 has the combination of powers. So we have a number already raised to the power x, and now ultimately raised to another power y. Look at that. So here, the law says we multiply out the powers. The powers have to combine. So this is the law that combines powers. A will be raised to a new power given by the product of the original powers. So x multiplies y to give us xy, the new power. Very simple. X times y gives us the new power, which is xy. So we have an example. 2 to the power 3. Now the arrangement being squared. How do we deal with this? The powers must combine by multiplication. And let's get into it. This is going to give us the same number 2 to the power. The 3 multiplies 2. 3 times 2, that gives us 6. And this means 2 multiplying itself to multiply itself 6 times gives us 64. Very simple. 64. Very simple. Let's move on. Let's move on. We have more sophisticated examples much later, but now we're simply building on the laws. So the next law, law 5, traces out of the way. All right, law 5. Law 5 is a law that addresses fractional powers. Suppose we have a base A raised to a power which is a fraction, x over y. You can see that. A number raised to power fraction. Now, how do we go about this? The denominator in the power tells us the type of root that we're going to take. And the numerator, x in the power, tells us the power to which we're going to raise the arrangement of roots that we have taken. So this is going to give us the denominator in the power is y. So we're going to take the yth root. Yth root of that base A, all of this arrangement raised to the power in the numerator, which is x. So this is the evaluation. Very simple. So once we have the fractional power, the denominator in the fraction tells us the type of root we're going to take, and the numerator in the power tells us the power to which we're going to raise that arrangement of roots. Supposing we have an example here, 8 raised to the power 2/3, 2 over 3. How do we go about this? We inspect the denominator. The denominator in the power is 3. That means we're going to take the cube root. The denominator tells us the type of root we're going to take. And the numerator in the power is 2. It tells us the power to which we're going to raise that arrangement of roots that we have taken. So let's evaluate this. This is going to give us, since we have 3, we're taking the cube root of the base, the cube root of 8. Now the whole arrangement will be raised to the power 2. As a general principle here, we should evaluate the expression in the bracket first. And that means we are talking about cube root of 8. Simply, which number multiplies itself 3 times to give us 8. Which number multiplies itself 3 times to give us 8? And of course, that is 2. 2 multiplies itself 3 different times to give 8. Let's try it out. 2 multiplied by 2, that gives us 4. That 4 resulting multiplied by 2 gives us 8. Beautiful. Which means the cube root of 8 is simply 2. And now that 2 is the number being raised to the power 2, which is this power out here. So evaluation of the inner bracket, cube root of 8 is this 2, and that 2 is being raised to power 2 outside. 2 to the power 2, 2 multiplying itself, and that gives us 2 times 2, which is 4. Very simple. Supposing we have another example. For example, we have 9 to the power 2 over 3. 9 to the power 3 over 2. 9 to the power 3 over 2. We have this. Let's look at this. The denominator in the power tells us the type of root we're going to take. And the numerator in the power tells us the power, new power, to which we're going to raise that arrangement of roots. So this means if we evaluate this according to our law, we're going to take square root of the number because 2 is in the denominator. It tells us the type of root. So we're taking the square root. As a common practice, we do not have to write the 2 here. Since the square root is the simplest type of root, it's like raising a number to the power 1. We need not necessarily write the power 1, since the simplest power of a number, which is non-zero, is actually 1. So it's the same as 5. So the square root of 9 can be written that way, now to the power in the numerator, which is 3. And last, let's have this evaluated. The square root of 9 in the bracket, what number will multiply itself 2 times to give 9? And that is 3, of course. 3 times 3 gives 9. And this 3 raised to the power 3 outwards. And 3 multiplying itself in 3 different places. Can you figure it out? 3 multiplied by 3, multiplied by yet another 3. 3 times 3 is 9. 9 resulting times 3 gives us 27. So we have our final answer as 27. Very simple. That's the law. End of this law 5. Okay, so let's move on, pick up the next law. It is getting exciting, of course. Very interesting. Very, very interesting. Let's go. All right. So the next law. This law talks about distribution of powers also. So we want to have a product of 2 numbers, for example, AB, now raised to the power x. Look at this, AB raised to the power x. So the law of indices says we can distribute the power to the components in the bracket. All right, so we can take A and have the power x on it, multiplied also by B to the power the same x on it. Now, this law is reversible, of course. This law is reversible, of course. So we can go the reverse way. We can have, maybe we have P to the power M multiplied by another number Q to the power the same M. Look at that. The powers are the same. So long as these powers are the same, we can do a combination. And then they have the same power M. So we take the product, P times Q in the bracket. P times Q gives us PQ. Now to the common power M they both have. So our behavior in problems depends on what we intend to achieve. We can combine a product of 2 different numbers raised to the same power. Yes, of course. And then we can split them if we want. So here, this is the splitting rule. We split 2 numbers, A and B, having the same power x on them. And this is the combination. We can combine P and Q and maintain the same power to which each of them has been raised from the beginning. All right. So examples will come up regarding this law in due course. Come with me. Let's go on. The next law. The next law is a very beautiful law, of course. I call it the mobility law. The mobility law. This law is applied when we have a negative power, a to the power negative x. And I call it the mobility rule. So long as a number is raised to a power that is negative, then it becomes mobile. Now, already written as a numerator, the number can become a denominator that way. So we have it sinks as 1 over ordinary a to the power x, and the minus sign is gone. This is a law. So the presence of the negative sign in the power gives the number the capacity to move. Now, if it was originally a numerator, then it becomes a denominator. And now, if we have it as a denominator, for example, a constant k on top of the number a to the power negative x, look at that. Now, the number has a negative power. But being in the denominator position, we have to return it to go into the numerator area, and that means we're going to have k, our constant is still there, life, now receive a to the power, and the minus sign has been employed in the movement. So no minus anymore, we have ordinary x. Mobility rule. So if we have something like 8x to the power negative 3, we can simply write. We have a negative power in the x, so we can simply send this downwards or downstairs, and it becomes 8 retained in the numerator position divided by x to the power ordinary 3, no minus attached. And now if we have 9 on p squared, p to the power minus 2 rather, so that we have the minus, we can decide there is a minus sign in the power, and that guarantees the movement back into the numerator position. So we can now have p, 9, of course, then p joins as p to the power ordinary 2. The minus has been employed in the movement. So this is, I refer to this as the mobility. Mobility. A negative power guarantees a movement from denominator position into numerator position and vice versa. All right, let's move on. Another law. All right, so the traces we have to go so that we have this law. In this law, we have a fraction. We have a fraction. So this, we also, we decide to separate this out as a single law because it helps. Supposing we have a divided by b, and the arrangement raised to the power negative x. Look at that. Here comes the negative power again. Here comes the negative power. You can see that. Here, because of the minus in the power, we can swap positions. That which was originally the numerator gets into the denominator position, and that which was originally the denominator gets into the numerator position. So we have eventually b originally downwards or downstairs, go upstairs. A originally upstairs, come downstairs. And there is no more negative sign in the power. Such a beautiful law. So we're going to see this in applications. All right. Now come with me. The next is to look at a series of examples. Let's go. Now you can pause this video. You can pause this video and really take a look at some of these laws that we have studied. Review these laws before we get into examples. That is allowed. You can pause the video, go back to the laws, review them because we're about to apply them in examples. So come with me as we move on into examples. Some illustrative examples ready now. So we need clear space. Yes, of course, the first one. Let's get into it straight away. 25/4. 25/4, all to the power 3/2. So I'm going to rewrite that. Now I'll use the better color of marker. For contrast, so I have 25/4, all raised to the power negative 3/2. So you can begin to imagine the laws we're going to apply here. The negative sign in the power, which is the most recent law we just studied, requires the change of the position of numerator and denominator. Do you remember? We just studied this a moment ago. So this means 4 move upstairs and 25 sink downstairs. And now no more minus in the power. So we have ordinary 3/2. Beautiful. This is beautiful. Look at that. Now we have the fractional power, which is one of the laws we studied today. The number in the denominator tells us the type of root we're going to take. The type of root we're going to take. And the number in the numerator tells us the power we're going to take. Raise the arrangement to. So the type of root we're going to take and then power to which we're going to raise that arrangement. Let's go straight off into it. Square root, of course. 2 is in the denominator. It means we're going to take the square root. We don't need to write it 2, of course, as we have studied. 4 over 25. This is the arrangement. Now, this arrangement will be raised to the power in the numerator, which is 3. Beautiful. Now, start the action from the inner bracket, of course. The square root of 4 is 2, which number will multiply itself 2 times to give 4, and that is 2. The square root of 25 is also 5. That's right. So 5 multiplies itself to give 25. And therefore, this arrangement is raised to the power 3. This arrangement is raised to the power 3. So we can raise each one to the power 3. That means we're going to have 2 will be raised to the power 3. Let's go. 2 multiplies itself 3 times. 2 to the power 3, 2 times 2, 4 times 2, another one, 8. Divided by 5 to the power 3 also. 5 times 5, 25. Multiplied by 5 again, which is 125. Very simple. So that's very simple, of course. Now, let us move on with another law. So the high points again, the main area, interchange of 4 and 25, and then losing the minus sign. And now the fractional power requires the denominator to dictate the type of roots. The numerator tells us the power to which we raise the arrangement. That was done right there. And then evaluation of the square roots, and then concomitant raising both numerator and denominator to the power 3. That's right. Let's move on with the next example. All right, here we are. All right, the same pattern. You can pause the video and try this out. Yes. Okay. So we can write this as 8 over 27 raised to the power negative 2 over 3. And now we have a minus that we can't erase, except we make use of it. And right away, we're going to make use of it. Can you remember what will happen? Yes, of course. Interchange of the numerator and denominator. So 27 upstairs divided by 8 downstairs. All of these raised to power, the fraction gets out of the way. Fraction out of the way. So we have ordinary 2 over 3 prevailing. What does this tell us? Can you remember? The denominator tells us the type of root we're going to take. The numerator tells us the power to which we're going to raise that arrangement of roots. So we have, this is going to give us the type of roots. 3 tells us cube root. So we have cube root that we have to write. It's not the simplest root we know. Cube root of the arrangement, 27 divided by 8. All of this raised to the power, the number on top, which is 2. Now let us evaluate this. And this is going to give us, now cube root of 27, what number will multiply itself 3 times to give 27? Of course, that is 3. And cube root of 8, what number will multiply itself 3 times to give 8? And of course, that is 2. This retained to the power 2. And now we have to evaluate each of them. Numerator raised to the power 2, denominator also raised to that power 2. So 3 raised to the power 2, 3 squared, that's 9. Divided by 2 raised to the power 2, 2 squared, that's 4. This is the final answer, of course. Or would you like a mixed fraction? Then 4 divides into 9, that's 2 times, with a remainder of 1 over the original 4. Our final answer. Very simple. It's very simple, of course. Let's move into the next example. Beautiful. Now, this is a binary expression, of course. We have 5 to the power 0 plus 8 to the power negative 1 over 3. All these arrangements squared. So let us evaluate each expression in the bracket. Now we start straight off. You know the law, any number raised to the power 0 is actually 1. Of course, 5 to the power 0 is 1. Our first law in this session. Plus 8 is raised to power negative. And you know what that means? Come up with straight away 1 over 8 to the power 1 over 3. And that will be 8 to the power 1 over 3. The minus sign is no more there. So we have all of these raised to the power 2. Very simple. Now let's move on. Where is the pressure area in this work? Of course, so when you solve mixed problems, you always go to the pressure point where a principle needs to be applied. And this straight away is going to give us 1 plus 1 over, so what is the principle here? What's the principle here? Of course, it's an extension of that same law. That will tell us we have a cube root. The cube root of 8 raised to the power 1 in the numerator, which is simply the same value. Power 1 does not make any significant change. And this is going to give us, of course, 1 plus 1 over, what is the cube root of 8? We've been through this. What number will multiply itself 3 times to give 8? And that is 2. Beautiful. And let us not forget our power 2, of course. Now, if you watch my video on fractions, you will see I presented a principle right there. 1 plus any fraction. 1 plus any fraction at all. Simply, the result is numerator plus denominator. Add these two. 2 plus 1, which is 3. Over, place that on the existing denominator, which is 2, straight away. Even if you have 1 plus 7 over 9, same principle. Simply go numerator plus denominator, 7 plus 9, that's 16, over that same 9. So long as you're adding to 1, it's under fractions. So look for the video on fractions and learn. So this is going to give us 3 over 2, all of these squared. And now we're familiar with this. We're going to square both top and bottom. 3 squared on top, 9. 2 squared below, which is 4. Our final answer. Very simple. Let us move on. The next example. All right. Once again, we have a mixture. So we have 3 different areas. So we have that 0.12 to the power minus 1 and 4 to the power negative 1 over 2. Beautiful. So we're going to deal with each one according to their structure. So this is going to give us straight away. I go with 216 to the power 1 over 3. This is a fractional power, of course. 3 tells us the type of root we're going to take. So we're taking the cube root of 216 raised to the power 1. So I'm not going to have to show that for obvious reasons that you have learned in this video. Now multiply by, the first thing to do for 0.12 is to express it as a fraction. And in my video on decimals, conversion of decimals into fractions, I taught the principle here. Simply write the significant digit without the decimal point. This beginning 0 is not significant. So we simply write 12, place that over 1, and find out how many digits after the decimal point. 1, 2, which means we're going to have 2 zeros. That's it. That's the fractional equivalent of 0.12. Now all of this raised to power minus 1. Then multiply by, here we have negative power here, negative power. Can you see that? So it means mobility rule applied here, which means 1 over ordinary 4 to the power half. Now deal with the pressure areas. So we have that in different problems here. Now, which number will multiply itself 3 times? Cube root of 216 to give 216. Which number will multiply itself 3 times to give 216? So you can try them out. Can it be 2? No, that's 8. Can it be 3 to the power 3? That gives 27. Can it be 4? 4 multiplying itself 3 times gives 64. Can it be 5? 5 multiplying itself 3 times gives 125. Can it now be 6? So test that out. Can 6 multiply itself 3 times to give 216? Let's try it. 6 multiplied by 6 gives us 36. The 36 multiplied by 6 actually 216, which means the cube root of 216 is actually 6. Very simple there. Then multiply by, now let's still apply one more law. We have the negative in the power, and that tells you what you do right away. Interchange of numerator and denominator. So 100 moves upstairs, 12 moves downstairs. And this to the power 1, which I don't have to write, for obvious reasons, of course. Raised to power 1, we don't have to write that. So save that time. Divided by 1 divided by 4 to power half, we have, of course, a fractional power there. So it tells us we're going to take the square root of 4 and raise it to power 1 as we have learned in this video. Let's take a moment and evaluate further. Be patient with it. 6 multiplied by 100 divided by 12. Now multiplied by 1 divided by the square root of 4 is 2, actually. And now we can simplify by division of common factors. So let's go. 6 straight away divides into 12 2 times. And 2 multiplied by 2 is actually 4. So 2 multiplied by 2 is 4. That means the 4 resulting from this multiplication divides into 100 to give us 25. If you don't find it easy to do that, you can go digit by digit. 4 divides into 10, that's 2 times, which is 4 by 2, 8. Remainder 2. 2 by the side of 0 here, 20. 4 goes in 20, and that is 5. So prevalent figure, 25 times 1, gives us the final answer, which is 25. Very simple. Very simple. All right. So each problem was, each area of this problem was handled separately with different rules. 216 to the power 1 over 3. Eventually, we developed 6 there. 0.12 to the power minus 1, eventually, 100 divided by 12. 4 to the power minus half, eventually gave us 1 over square root of 4, and then we were able to pull this through. All right. So let us take on the next example. So come with me and stay with me. Now, 2 important steps to be taken right now. If you have not yet subscribed to this channel, please subscribe now to this channel. And more than subscription, turn on the notification bell so that you know when I make a new video in this channel. This channel has videos on the science subject, biology, chemistry, and physics. Has videos on mathematics, has videos on chess, inspirational narrations, motivational narrations. So, and then handwriting training. So this is a very, very resourceful channel. So please subscribe, turn on the notification bell so that you can get notifications when new videos are uploaded on this channel. Thank you. We move on. More examples, let's go. So we have 3 raised to the power 2n plus 1 in the numerator. Multiplied by 6 raised to the power 2n, multiplied again by 4 raised to the power n, now divided by 16 raised to the power n, multiplied by 9 to the power 2n. This is what we've got. Now we can begin straight away. And a quick inspection of this problem shows that the numbers here can be broken into 3 and 2 to contain 3 and 2. And that's what we do straight away. So let us have this as 3 raised to the power 2n plus 1. Let's hold our piece there. 3 to the power 2n plus 1 multiplied by, now the 6 right there. The 6 in that position can be broken into 3 multiplied by 2. So let's do that. That means 6 is actually 3 multiplied by 2, 3 multiplied by 2, all, both of them to the power 2n. And multiplied by the 4 right there is actually 2 to the power 2, then with the n attached. Divided by, do the same thing in the denominator, simplify the denominator appropriately. 16 means 2 to the power 4. To multiply itself 4 different times gives 16. And now we have the power n there. Multiplied by 9, of course. That 9 right there is actually 3 squared. So we can write 9 as 3 to the power 2. Then the arrangement is raised to the power 2n. This is the new phase of the problem now. So let us continue in this area. Let's continue. Now, let's expose these powers, of course. Let's expose these powers. So we have, and at the same time, break this up. This is a law we already know. It came from the combination law. So let us have the same base, which is 3, raised to power, these 2 powers, multiply together. Okay, this is what we mean. 3 to the power 2n multiplied by 3 to the power 1. Of course. So this is the original writing that gave rise to 3 to the power 2n plus 1. We have maintained the same base 3 in each case, and then we have retained the power 2n and 1, okay, on the 3. And now we multiply by, in the second area, of course, we can distribute the powers. This is one of the laws we studied in this video. The 3 can receive the power 2n on it, multiplied by 2 also can receive the power 2n on it, and finally multiply by the last area, which is the 2 can be exposed to multiply the n. So we have 2 to the power 2n. Beautiful. And now some activity in the denominator also. We have 2 raised to the power 4, and n will interact by multiplying. 4 multiplied by n is 4n. Now times, we have 3 to the power, the 2 will multiply 2n. 2 multiplied by 2n generates 4n. Beautiful. So we're getting through. All the numbers here are expressed in terms of either 3 or 2. Now combination can occur. So let's begin the combination process. Let us take all. So this is going to give us 3. In the numerator, let us combine all the 3's. So we have, this is 3, a term in 3 right there. So let me highlight all of them. That is 3 to a power. That is 3 to a power. That is 3 to a power. 3 of them. But now, a quick inspection. I would like to leave the one that doesn't have n. So let us combine those that have n. So what do we mean by that? Let us take on 2n added to just this 2n here. 2n plus 2n gives us 4n. While we retain ordinary 3 to the power 1, which is simply 3. Beautiful. It's a good combination. Now multiply by combining 2 in the same way. So we have, once again, that is 2. Can you figure it out? That is 2 again. And that is 2 to the power. So we can combine this also. Let's do the combination. We have ordinary 2, the same base to which they've been written. And now we have to add the powers. 2n plus 2n. Combination law says we add the powers. 2n plus 2n gives us 4n. And now we can retain the denominator the way they are. 2 to the power 4n. Combination has already been done here. Multiply by 3 to the power 4n. Now, let us inspect the numerator and denominator. Elimination of similar terms. 2 to the power 4n divides into 2 to the power 4n. Total elimination there. 3 to the power 4n divides into 3 to the power 4n. And of course, the prevailing figure is simply 3. Very simple. That's right. Very simple. All right. So let us proceed. We have, so the high points, once again, the splitting of the numbers in terms of 2 and 3, and then the combination of the 3's and the 2's, and then ultimate simplification. So come with me. We're looking at another example right away. Get the traces out of the way. Of course, very simple. 3 to the power x multiplied by 9 to the power x minus 1, now divided by 27 to the power x plus 1. Now, a quick inspection of this problem shows that every number here can be expressed in terms of 3. Now, look at that. We have 3 to the power x here. It is 3 being raised to the power. We have 9, which is actually 3 to the power 2. Can you figure that out? And we have 27, which is actually 3 to the power 3. You can also figure that out. So, doing a new writing, we can have just 3 to the power x in the first area. Now multiply by 9 there, and 9 is actually 3 squared. 3 squared for that 9, and all of it is now raised to the power x minus 1. Can you see that? Now divided by the same thing in the denominator. 27 is actually 3 to the power 3, and all of that is being raised to the power x plus 1 outwards. Very simple. Now let us do the combination of the power. So we have to combine this area. Yes. Combine that area by multiplying the powers. And of course, combine this area multiplying the powers. The same operations. Let's get into it. So this is going to give us, it is equal to 3 to the power x, taking note of that term, multiplied by, let's have this. This is 3 to the power 2 has to multiply the whole arrangement x minus 1 that way. Divided by in the denominator, 3 to the power 3 also has to multiply the whole of x plus 1. Beautiful. And now let us do the expansion of the brackets. So we have, this is going to be 3 to the power x multiplied by 3 to the power, now it's the time to get into the bracket by expansion. 2 will multiply each term in the brackets. Let's go. 2 multiplied by x, 2x. And 2 times minus 1, minus 2. In the denominator, of course, same operation. We have 3 raised to the power 3 multiplied by x, 3x. That's right. Plus 3 multiplied by 1, and that is 3. Let us take a moment to combine the terms in the numerator. So this is going to give us, we have the law of indices, the combination law. We have 3 to the power and 3 to the power. So we decide to go along with just one of the 3's to a power that requires combination of the existing ones. So let's have x added to the second power plus 2x minus 2. All of this divided by, in the denominator, we have 3 to the power 3x plus 3. And now let us do the combination. So this is going to give us, this is going to give us 3 to the power, let's go, the like terms, x plus 2x, that is 1x plus 2x, gives us 3x. Then minus 2. Now divided by 3 to the power the same, 3x, then plus 3. And now let's do the relocation of terms. We have 3 to the power and 3 to the power. So we have this as one of our combination laws, the same 3 in the numerator but raised to different powers. How do we proceed? We take the same 3, the power in the numerator must subtract the power in the denominator. So we have all of 3x minus 2. We subtract, and now the critical moment. Anytime you attempt to subtract a binary expression containing more than one term or more, a bracket is necessary, else we'll be wrong. So this is 3x plus 3, which means the whole expression is being subtracted. Very important. Let us now expand the bracket with the minus. So we have, this is going to be 3 to the power 3x minus 2. Now expand the bracket, minus opens up the bracket, minus changes all the signs. Minus times 3x, minus 3x, and of course, minus times plus 3, minus 3. And now we can allow like terms to interact. And this is going to give us 3 raised to the power 3x minus 3x leaves us with a 0 term in x. And of course, we don't need to write that. 3x minus 3x, 0 term in x, 0x. So we leave that and now go in for minus 2, minus 3. You can see that, minus 2, minus 3, and that gives us minus 5. Now let us finish it off in this area. 3 to the power negative 5, this is our mobility rule. The minus being in the power requires us to relocate into the denominator area. So we're going to have 1 over 3 to the power, no more minus around the 5, just 5. 1 over 3 to the power 5. And now the final knockout, the final answer, 1 over 3 multiply itself 5 times. That will give us 243, of course, our final answer. Very simple. 3 multiplying itself 5 different times. Let's go. 3 times 3 times 3 times 3 and times a final 3. Let's go. 3 times 3, that's 9. That 9 resulting times 3. That's 27. The 27 resulting times 3, that's 81. 81 times 3, of course, 243, our final answer. Very simple. So the high points, once again, every number in the original problem can be expressed in terms of 3, and we went straight off for that. 3 to the power, 3 to the power, and 3 to the power for 27. Now, powers interact by expansion of brackets, of course, combination of like terms with evaluation, bringing us to this simplified state. And now the main area, the critical moment, that moment where the numerator subtracted the denominator with the recognition of the minus present before the bracket. Without this move, we could be wrong. Now the ultimate expansion and expression of the final answer. Very simple. Come with me, we'll move on into the next example. All right. Now we have, this is a more involved problem. We have the cube root of a product x and y divided by x to the power 1/6 and y to the power 2/3, expressed in the form x to the power alpha divided by y to the power beta. And we want to find alpha comma beta. This is very beautiful. Now, we start straight off by decoupling the problem. So let us break it up. And this is going to be, I have straight away a reversal of the fractional power law. So x and y, that combination has to be raised to power 1/3. And this is how the cube root came, of course. So a reverse. Now divide by x to the power 1/6. And of course, y to the power 2/3. All of this equals our normal x to the power alpha and y to the power beta. This is beautiful. Now let's distribute the powers in the numerator, because our target is to express the left-hand side in the format of the right-hand side. You can see the format of the right-hand side is x to a given power divided by y to another power, and we must achieve that. So this means don't have two equalities in this problem. So it is therefore, if we must write anything there, it is therefore, right? So it is therefore, if we must write anything here, that means we have distribution of this power. So the 1/3 as power should be distributed onto the x and the y. That means we're going to have x to the power 1/3, and of course y to the power 1/3. Now divided by ordinary x to the power 1/6, and of course y to the power 2/3. Gives us x to the power alpha, and of course y to the power beta. Beautiful. Now let us allow the numbers to interact. So we have, since x forms the numerator, look at that, x forms the numerator and y forms the denominator. Let us have all terms involving x to stay in the numerator area. That means the x to the power 1/6 has to relocate to join x to the power 1/3 upstairs. Y is in the denominator area. That means the y to the power 1/3 should be made also to join y to the power 2/3 in the denominator. Let's do this very quickly. It means up here we're going to have x to the power 1/3. That is this term already existing. That is this particular term. That is this term existing here. Yes. So this term should welcome the arrival of x to the power 1/6. X to the power 1/6 should join, multiply by, and of course, the law we already know. For x to the power 1/6 to move into the numerator area, it will have the sign of the power change. 1/6 into minus 1/6. It is important to understand this before we move on. X to the power 1/6 moves up the sign of the power we change from 1/6 into minus 1/6. Now divide by. We already have resident in the bottom, the y to the power 2/3. Let us keep it as y to the power 2/3. Resident already in the bottom. Now we want y to the power 1/3 to join it. That's right. Now, if there's movement from this numerator area into the denominator area, then y to the power 1/3 will have its sign change. The power we have its sign change, negative 1/3. That's right. And all of this will give us x to the power alpha divided by y to the power beta. Beautiful. So we have the format of the left-hand side right there. We have the format of the left-hand side right here. Very simple. Now let's move on. So we're going to use the laws of indices to combine the numerator and denominator, of course. So this is a way of writing times. Of course, there is times in between them. It can be written as that dot. Now let's go straight off for it. Therefore, we have the combination law being applied. X to the power 1/3 plus because they are multiplying, and we're adding a power which is negative, -1/6, divided by the same thing with y. So we have y, and their powers will interact, the same order, so 2/3, plus, and what we have to add is -1/3. All of this with the structure on the right, x to the power alpha divided by y to the power beta. The same. Beautiful. Now, let's allow the two signs to interact. Plus times minus is always minus. So this is going to give us x to the power 1/3 minus 1/6. All of this divided by y to the power 2/3 minus 1/3, as you can see, is equal now to x to the power alpha divided by y to the power beta. Very interesting and beautiful. So let us buy a little more space here to finish it off. Now, we're going to have to do the combination of this fraction. So 1/3 minus 1/6, can you figure it out? Find the LCM. 1/3 minus 1/6. Can you find the LCM? So this is going to give us 1/. Let's go. If we have to find or make a short trick that I showed in my video on fractions here, 1/3 can be written as 2/6 here. Can you imagine that? 1/3 is the same as 2/6. Yes. If you multiply both numerator and denominator by 2, and if you divide, 2 divides into 6 restores 1/3. So view 1/3 as 2/6 here. And now, because they now have the same denominator, we can simply go 2 minus 1, which is 1, divided by 6. Or you can simply find LCM your usual way. 1/3 minus 1/6, you're going to get 1/6. That means you have x to the power 1/6 in the numerator, divided by the same thing. Determine the power on y. The power on y is going to be the 2/3 now minus 1/3. And look at that, they have the same denominator. In my video on fractions, I showed how to handle this. Since they have the same denominator, the result will be that same denominator maintained, but now interaction of the numerators after the order of the separating signs. So 2 minus 1 gives 1 straight away. So we have y to the power 1/3. Y is to the power 1/3. Y to the power 1/3 gives us the right-hand side, which is x to the power alpha divided by y to the power beta. And now, by comparing both sides, this is by comparison, x to the power, x to the power. By comparing both sides, the powers on the numerator will match the power on the numerator on both sides. The power on the denominator will match the power on the denominator on both sides. This implies very quickly, as written, alpha comma beta is the same as alpha represents 1/6 the power, beta represents 1/3. So we can have 1/6 comma as written, 1/3, our final answer. Very simple. Please study this problem carefully. Pause the video, study this problem, make a note on it, repeat it, and of course, it is very clear. All right, let's take on the next one. All right. Okay, it is your time to practice. It's your turn to practice. I've got practice for you in this video. And that's the only way you can become an expert, of course. Solve. So the first and then the second question, you have to solve this. Next ones, you have solved. As you can see, we solve this. Find the value of P or Q in this case. So this is another one. So pause the video to solve all of this. Another one. So you're going to find this interesting. And the answer key is up next. Are you ready? So I'm flashing that very fast. Yes. Now mastery and expertise are product of persistence. Consistency in practice. This is the only way you can become sound by practice. So I encourage authority to practice. Thank you for being part of the session. So I look forward to seeing you in another video. So subscribe to this channel and follow me on YouTube, Facebook, Instagram, chess.com, TikTok, LinkedIn. And if you like to send a WhatsApp message, that's my number on WhatsApp. Like to send a WhatsApp message, that's my number. And you can also send a mail. And of course, if you like to look out for some of my publications on Amazon, so just go to Amazon and type Template. You see a lot of books I've written, very beautiful books. Please subscribe, like, share, and make a comment to engage. Thanks for being part of the session. I'm your regular coach.